Tudo bom, Igor? Pode começar? Em português. Boa tarde a todos. Então, hoje nós vamos ter um seminário extra aqui do departamento, que o professor Tércio Ambrisi solicitou para o Dr. Nick Hall, que é da Universidade de Toulouse, e atualmente está passando um período na FUNSEMI, né? E ele vai falar para a gente sobre previsões sazonais para o Nordeste do Brasil. Então, eu queria agradecer ao professor Nick por vir aqui dar esse seminário. Queria agradecer muito ao público, né, que hoje é um seminário extra. E vamos... Ô, Nick, como tem muita gente tem aula, então, se você puder ser não muito prolongar muito o seminário, uns 35, 40 minutos, para ter algumas perguntas. Eu dou aulas duas, o Ralph, bastante gente tem aulas duas. Okay?
Você pode me ligar para
okay, I don't know if you speak in Portuguese or in English.
Prefere seminário de 50 minutos em inglês ou em português, 2, 3 horas, 4 horas? Que prefere?
You can decide.
No, I'm going to speak English. Is this working? Yeah, it's working. Yeah, so I'm going to give a seminar in English. My Portuguese is always improving, but very slowly, and it's tending exponentially to a very low level. So yeah, this is, I came here about a year ago, something like that, and gave a quick talk about my forecasting activity in FUNSEMI, and showed you my forecast for 2022. Yeah. And this seminar will explain to you just how wrong that was and how much we've improved, or we've tried to improve since. Because our objective is to build a kind of cheap, economical, cost-effective forecast system for rainfall in northeast Brazil. And we're doing this using the DREAM model, which is it's essentially a dynamical model, which we are trying to apply to the seasonal forecast problem. DREAM stands for Dynamical Research Empirical Atmospheric Model. Keyword here is empirical, which I'll explain in a minute, but it means that some of the physics has been removed and replaced by empirically derived forcing functions. So this is my dream team here in Fortaleza. I don't think of them as a research group. I think of them more as a Formula One racing team. So I'm the team principal. This is my driver, Junior. He's in charge of running the model. This is the engineer, Obens. He's in charge of sea surface temperatures. And this is our strategist, Leticia. She's in charge of diagnostics and evaluation. Okay, so this is the forecast that I issued a little bit more than a year ago, at the beginning of 2022. And we made a little bit of a publicity buzz about this forecast because it was the first time, we made a seasonal forecast with a simple model. And this is what we predicted for the rainy season in the Northeast. That should say February, March, April. Sorry about that. Anyway, the rainy season in the Northeast. And we predicted it would be wet over the Northeast, wet in the North Tropical Atlantic, dry in the South Tropical Atlantic, dry up here, wet down here over Uruguay. And so that's our prediction. It's the result of an ensemble, 38 members, different initial conditions. And this is what actually happened. So the question is that a good forecast, right? At the time, we're thinking, yeah, this is great. This has worked, right? Because look, I should be using this thing, shouldn't I? Sorry. Yeah. So yeah, we've got wet in the tropical North Atlantic. That's okay. Dry in the tropical South Atlantic. That's okay. sort of wet over the northeast Amazon region. Well, sort of. This dry patch here seems to be okay. This is completely wrong here. This wet here actually turned out to be dry. And way down here, we sort of got a wet patch. So if it's a good forecast or not depends really on where you live. And the question is, how well did we do? Did we actually make a good forecast because it's a good forecast model? How much does this really mean, this apparent success? So the next thing we did after we'd issued this forecast was to go back. Well, before I tell you about that, this is what we do. Okay, this is our forecast system. So this is a kind of generic scheme for seasonal forecasting, right? So you're solving a dynamical physical problem. So you've basically got a tendency of whatever, okay? And it depends on the fluid dynamics of the atmosphere. And it also depends on atmospheric physics, right? So that's all. So this is all your advection operators, okay? And this is things like boundary fluxes, radiation, all the things which get called physics in a GCM. And that kind of forces this equation. And there's also some dissipation. So we have advection, forcing, and dissipation. And if you start with an initial condition, then you will end up with a result, okay? But because it's a seasonal forecast, we need to explore the range of possibilities. So we need to have an ensemble of many initial conditions to give an ensemble of results. And then the ensemble mean is usually our forecast, but we can also assess the distributions and the probabilities. Now, that is a normal forecast, right? But if it's a seasonal forecast, that means we're starting at the beginning of January, and we're running for about 5 months, okay, to get to the end of May. And there's no way you can make a forecast for that length of time just from the initial conditions. So what we need is something which will give us some information. And the key here is the sea surface temperatures, because that is the element of the system that has some memory. It's the slow element of the system. If you assume that the anomaly in the sea surface temperature at the beginning of the forecast will persist, that's a reasonably good assumption, and it gives you some useful information to make the forecast with. So that also feeds into this. So this is all what most forecasting centers do, right? And they do this in FUNSEMI as well. They use the ECAM GCM, and they do 20-member ensembles for 5 months. And to run one member for 1 month takes 1 hour of computer time on the FUNSEMI system, right? So, like 20 members for 5 months, that's 100 hours. So it's going to take several days, something like a week, to do this forecast, right? So this is where the DREAM system comes in. With DREAM, we bypass the expensive part, which is the atmospheric physics, and replace it with an empirical forcing function, which is derived from a large data set. Okay, and I've spoken many times about how we do that, but I'm not going to go into details today. But it's a bit like artificial intelligence, but without the intelligence, okay? It's just an empirical forcing function. And if we do that with our DREAM model, 1 month, single member forecast takes 1 minute, okay? So we can run the entire seasonal forecast in a couple of hours instead of a week. Right? Now this gives us flexibility to do lots of different tests of concepts. So it's a useful academic test model. Is it a useful forecast model? That's the question, right? So how good was that forecast really, the one I just showed you? So we went back to 1982 and we repeated the exercise for every year from 1982 to 2020. Okay? Now with DREAM, you can do that quite quickly. It just takes a day or so, right? And this is what we got. So the dashed curve is the rainfall anomaly over this box here. Oh God, I've lost it. Going too fast. The box here in the northeast of Brazil, right? The mean rainfall anomaly from the climatology. And the box plots are the model ensemble. So we have a 38-member ensemble. And so the correlation coefficient between the model forecasts and the observed rainfall anomaly is very close to 0, okay? And if you do a contingency table, so along the bottom here is the terciles, so normal conditions, wet conditions, dry conditions, as predicted, and then as observed, normal, dry, wet. If you have a good model, you expect most of the points to be along this leading diagonal, right? So what we have is actually more points on the opposite diagonal. When the model says it's wet, it's dry. When the model says it's dry, it's wet. So that's a partial success, okay? I mean, you could use that as a forecast model. You just have to say the opposite of what the model is going to say. That's what's going to happen, right? Not very satisfactory. So if we go back to the question, was that a good forecast in 2022? The answer is, well, maybe, but it was luck, right? So what do, right? Well, let me explain a little bit how we translate information from the sea surface temperature to the atmosphere. What happens is that you have an anomaly in the sea surface temperature. It will change the conditions in the atmosphere, and essentially it'll create more or less deep convection in the tropics. And that deep convection will lead to heating anomalies in the troposphere, which will lead to a dynamical response, Kelvin waves, Rossby waves, and a general equilibrated response to the circulation, which is global, right? And that global response will then change the moisture flux convergence over the continent and will alter the rainfall over the continent. That's the theory. So what we did was to use an empirical approach for the SSTs. We thought, right, we need to link the local SST. So here's an example: moderate El Nino, strong El Nino, and La Nina. These SSTs, we need to link with the associated precipitation anomalies. We can impose those on the model, and then the model will react to those, and it'll use its own convection scheme to create anomalous precipitation over the continent. So we're kind of introducing artificially an anomalous precipitation into the model here. So this is the observed regressed precipitation associated with El Nino, moderate El Nino, strong El Nino, or La Nina, just as an example, right? And this is our transfer function. So I say, right, I want to calculate the precipitation anomaly. It depends on, here, the SST anomaly. It also depends on the climatological SST and on the climatological divergence because, well, it's nonlinear, right? So the same SST anomaly over warm water will give you a much bigger response than if it were over cold water, right? So the same SST anomaly over the Western Pacific would give you a much bigger response than if it was over the Eastern Pacific, for example. Also, if you have generally low-level divergence, then SST anomaly is not going to do very much. So that's our transfer function. This is the transfer function we used in those forecasts, and this is the associated estimate of the precipitation anomaly. You can see that it's not particularly good. I mean, this doesn't work very well with that. This doesn't look like that. So I thought to myself, this transfer function comes from theory. It comes from some colleagues of mine in France. It's not doing a very good job. That's why my forecast is not very good, right? So I thought I'm going to modify it. So I added some terms, added some parameters, okay, which allowed me to separate the sensitivity to the anomaly from the sensitivity to the climatological SST. And I tuned it to make it look good, and I came up with this, right? This looks more like this. This looks more like that, and this looks more like this. So my idea was that this is going to fix my forecast problem. Okay, so then we went back and did all the forecasts again. So remember, our correlation coefficient before was minus 0.03, but now look, it's minus 0.13. So that's another partial success, isn't it, really? And we always learn from our mistakes. But at this point, I'm thinking, I'm not going to carry on down this road. I mean, if you've tried and tried and tried on a scientific problem and it's going nowhere, don't keep on adding parameters and trying to figure out how to make it that little bit better. It's just not going to work, okay? So I thought what we need here is, instead of adding Ptolemaic epicycles, we need a Copernican revolution, right? It made me think of the philosophy of science. You know, Ptolemy had this idea that the planets went round in circles, but then it didn't work, so he added circles on the circles, and they even added circles on the circles on the circles. I don't want to do that. I want to do elliptical orbits, right? I want Copernicus, right? So I thought to myself, what do we do now? Where do we go from here? So it's all very well talking about ancient Greeks and philosophy of science, but personally, I'm not very familiar with philosophy. I'm much more interested in Formula One racing, as I said earlier, right? So I was watching a Formula One, and I don't know how much you know about Formula One, but in 2021, Lewis Hamilton should have been like 8 times champion, beating Michael Schumacher's record. But unfortunately, in the last race of the season, they cheated and they deprived him of his title, right? So the following year, he comes back and he's trying to win again, but they changed the rules of the regulations, and his car was not really very good. And unfortunately, Max Verstappen, who stole the title the previous year, actually walked away with the title and won it fair and square in 2022. And Mercedes, they're like, right, we've got a good concept, we're going to keep on developing it, right? Warning light. So gets to like May this springtime this year, and it's still not working. So I felt a lot of empathy with the director of the Mercedes Formula One team. Told, well, if we got the physics wrong, we have to start again from scratch. And then there's Lewis Hamilton here. He's saying like, yeah, I told you all along, the car's no good, right? In the meantime, Fernando Alonso is walking away with the silverware in an Aston Martin, which is actually powered with a Mercedes engine. How embarrassing is that? So this is, you know, time to rethink. And so we got, no, it's Junior, my driver. Yeah, and so we thought we're going to do something different. We're going to build an Aston Martin, right? This is the Aston Martin. This is the Mercedes. And the difference between the two of them is all about aerodynamics. And so what we did before was this anomaly concept for sea surface temperature anomalies. And it led to some slightly uncomfortable artifacts, like it's a kind of double counting. Sometimes you have negative precipitation, which is difficult to explain, right? So I thought, instead of this empirical transfer function, which I've explained to you, I'm going to go traditional. I'm just going to use the bottom boundary condition, modify the bottom boundary condition. So whatever the SST anomaly is, well, there's a diffusion scheme in the model. So the bottom boundary condition calculates a flux, which is the difference between the bottom layer and some hidden layer. I'm going to add that SST anomaly to the hidden layer and increase the flux. And I'll do the same thing with the humidity appropriately by adding the difference in saturated specific humidity associated with that SST anomaly. And let's see how we do with that, right? Because Toto Wolff is right, the stopwatch doesn't lie. Sometimes you have to go back to the drawing board, right? So because Formula One cars always all look the same as each other, here's a real Mercedes, you know, slightly used, and here's the British car, the Aston Martin DBS. And so this is my old model, and this is the new model. So the control simulation from the previous. So this is just a run with no SST anomalies to look at the rainfall climate. This is GPCP, and this is the new model where I've tweaked some of the parameters. So we've already improved the control climate quite a lot. Look, the ITCZ structure is much better. The Indonesian structure is a bit weak, but it's much more realistic in the distribution. And it's a bit wetter over Brazil than it was, which is one of our main systematic errors, right? So the control is all right. Let's do some tests. So I'm going to have a quick digression now onto what is our test bed, which is our wind tunnel for testing the machine, okay? And that will be various canonical sea surface temperature anomaly patterns, right? So we start with the same three: extreme El Nino, moderate El Nino, and La Nina. How do we pick those? Well, this is very interesting, right? If you take the variability month by month in the Pacific sea surface temperature, and you calculate EOFs of that, right? The first EOF here looks like El Nino. And the second EOF, unsurprisingly, is a kind of dipole from east to west. EOFs always do this, right? They always give you a potato for the first one and a dipole for the second. Unless it's a propagating system, in which case it gives you a dipole and a shifted dipole. But there's no surprise here. This is what EOFs do, right? Oops. Back. But what's interesting with the case of the Pacific is if you plot the scatter plot of the first EOF against the second, the distribution actually has a form to it. It's a kind of quadratic curve. Right? Now, people have been very excited about that in the literature for the last decade or so, talking about different kinds of El Nino, right? You've probably heard about Modoki El Nino, extreme El Nino, East Pacific El Nino, Central Pacific El Nino, whatever you want to call it. Basically, it depends on this relationship, right? And what happens is when the El Nino is very strong, it doesn't look like EOF1. It looks like EOF1 plus EOF2, which is an Eastern Pacific intensified El Nino. When it's a moderate El Nino, it basically looks like EOF1, right? And La Nina does not look like the opposite of EOF1. It looks like the opposite of EOF1 plus EOF2. So it's slightly shifted to the west compared to El Nino. And these three shapes are our canonical shapes for El Nino. So we thought, well, this has been published several times, right? But with O'Baines, we thought we'll have a go and see what we get. We got the same thing as everyone else, right? So we thought, let's try this in the Atlantic, because the Atlantic is important. So here's the first EOF in the Atlantic. It shows you where the variance is. It's in the upwelling regions, north of the equator and south of the equator. Right? And here's the second EOF. It's a dipole across the equator, right? But if you plot one against the other, what do you get? Absolutely nothing. There's no relationship whatsoever between these two EOFs, right? So we thought there's no structure here which corresponds to any physical behavior. This is just data compression. This is just EOFs doing what they do, which is to compress the data first into a monopole and then into a dipole. Or in this case, there's variance here. Look where the variance is, east of Senegal and east of Angola. And here, the variance is in the same places, right? They just flip the sign. What does that tell you? If you're used to looking at EOFs, be careful, right? Because this is a beautiful example of how EOFs do not correspond to any kind of physical mode of variability. They're just data compression. And so what's happening here is that there's a lot of variance here. There's a lot of variance here. Sometimes it's the same. Sometimes it's the opposite. And there's no correlation between the two, right? Of course, there can't possibly be a straight line in this graph because that would just be the first EOF. But there could be a quadratic curve, but there isn't, okay? Anyway, so we thought, well, let's just look at the regressions against the North Tropical Atlantic and the South Tropical Atlantic separately. And this is the regression pattern you get. Look at that. The regression against the SST in this box, there is no relationship whatsoever with the other side of the equator. To the other side of the equator, there's no relationship with the north side of the equator. You do have dipoles with the extratropics. There's no correlation or anti-correlation between one side of the tropic Atlantic and the other. So this famous tropical Atlantic dipole doesn't exist. Okay? There is no tropical Atlantic dipole mode of variability. It doesn't exist. That's interesting, right? Because a lot of people have written a lot about it. Anyway, so we decided we're just going to use these two patterns as our canonical test beds. And so let's try looking at the model reaction to a persisted canonical SST pattern. And so this is the old model. How does it react to persisted moderate El Nino? This is the regression of precipitation onto the moderate El Nino cases. And this is the new model. So if you look at the form of precipitation in the Pacific, it's slightly better with the new model. The old model is a bit extreme and a bit too far west. So it's a better shape, it's a bit weak. Over Brazil, you have this dry patch. And to be honest, the old model got that, and so does the new model, a little bit stronger. Okay, and in the Indian Ocean, the new model is better than the old one. So far, so good. It's slightly better, right? Extreme El Nino, very much the same story. In the Pacific, it's much better. So at least now we're forcing with the right kind of heating over the ocean, and the response over the continent is reasonably realistic. We don't get this southern wet patch, unfortunately, but we get the dry. We did that before, but now we got it stronger. Okay, and over here and in the Indian Ocean, this is much better than that. Okay, so 2 out of 2. La Nina. Well, La Nina, we've got a kind of very exaggerated response to La Nina, and much too far to the east with the old model. Now we've got something much more realistic with the new model. And that the response over South America is wet during La Nina, as we know for the last 2 years, it's been wet, right? And the model predicted dry over with a sort of dipole here. The new model, a bit weak, but wet, in fact. Okay, now, Atlantic. The tropical North Atlantic, what you get if you have a warm SST in the tropical North Atlantic, you get a dry slot across the equatorial Atlantic, just south of the equator, and dry conditions over nordeste, wet here. We kind of got that already with the old model, so the old model wasn't so bad with that. The new model is more realistic over the ocean, you have to say, slightly shifted south over the land compared to what it should be. We're still failing to get this wet response here. How about the tropical South Atlantic, last one? What you get normally by the regression is wet, okay, with the dry to the north. The old model basically got dry over Sierra, and now the new model is wet. So the new model is much better than the old model. So this gives us hope, okay, that it's going to work better. Here's the qualifying now. Now we're at qualifying. Now, this is the GPCP precipitation climatology again. And I'm showing you climatology again, but now it's not just from a long run without SSTs. Now it's from all of the forecast runs, from all of the years. And the average of that is not necessarily the same as the control run, because the response to SST anomalies is nonlinear, right? So if we look at the old model and the new model, there's clearly, again, the new model is superior to the old model. And I think that this is better than the model climatology, this long multi-forecast mean. These are the systematic errors, or the bias. You're a statistician. And basically the dry error over South America has been improved a bit. And it's basically improved a bit everywhere, right? These errors are smaller than these errors. In the climatology, right? What about the forecast? So now for the race, okay? So we're pitching an old Mercedes against a new Aston Martin. And remember, it was minus 0.13, the correlation coefficient we had before. And now it's positive 0.46. So that made me feel good when I saw that. I thought, at last, you know. And if you look at the correlation coefficient as a function of position for the rainfall, because this is in the northeast box, okay, these graphs. But this is the map of the correlation coefficient, and it's better everywhere, basically, in the new model. And importantly, it compares quite well with the actual GCM, ECAM, which, remember, is 60 times slower than DREAM, okay? So this is DREAM, this is ECAM, 0.46, 0.56. So we've still got a little bit of catching up to do, but so that's my German SUV. It's got a lot more versatility, but the Aston Martin is much faster. And so there, and our contingency tables now are looking a little bit more sloping in the right direction, you might say. So that's our new forecast model. And finally, the checkered flag. What is our forecast for 2023? Because at the beginning of 2023, we didn't make a big fuss about this, but now I can show you. Now, it's a bit late to be showing you the forecast for something that's already happened, but this is what our forecast was before. This is what it is now, right? It's completely different, and it's much better because it actually turned out to be a wet year, right? It's slightly different from ECAM, again, but at least they're not completely inconsistent. Right, so there you go. That's our forecasting activity. Where can we go from here, right? What about research? What can we do with this tool now? And so let's go back to another motoring analogy, if you like. Miles per gallon or liters per 100 kilometer. Now I grew up in England, where if you want to know about the fuel economy of your car, you talk about miles per gallon, right? And a good economical car would do about 40, a bit more than 40 miles per gallon, right? But now I live in France most of the time, where if you want to know about the fuel economy, it's liters per 100 kilometers, and a good car is about 5 or 6 liters per 100 kilometers, right? Now, what's the difference between these two units? Well, obviously one's in imperial and one's in metric, but that's not the point, right? The point is that your Englishman, he asks a different question to your Frenchman, right? The English guy, he says, right, I've got a full tank of petrol, but no idea where I'm going. How far can I get, right? The Frenchman, he knows exactly where he wants to go, and he wants to know how much it's going to cost him, right? Different questions, both legitimate, right? Completely different. And we can ask these questions in relation to SST anomalies and precipitation. Right? Now, this is the correlation coefficient between rainfall in this red box and the SST around the world. And it has no units. It's the covariance divided by the product of the two standard deviations. So it's a unitless correlation coefficient. That's what people normally look at. And if you look at that, you see that, well, if you want it to be wet in northeast Brazil, then it either has to be cold in the Pacific or cold in the North Tropical Atlantic or warm in the South Tropical Atlantic. And that is, you know, you can be forgiven looking at that for believing that there is actually such a thing as the tropical Atlantic dipole, but there isn't, okay? It can be either cold here or warm here or both or neither. They're completely independent. Each of them affects the rainfall in northeast Brazil, right? So again, I'd just like to, you know, caution you on the interpretation of empirical orthogonal functions, right? So how about if we look at this in a different way and we give it some units? So the units here, if we ask the question, how big an SST anomaly do you need for a given rainfall anomaly? So that's a bit like liters per 100 kilometer. That's the Frenchman. Okay? He's asking, I've got a certain amount of rainfall I need. How much is it going to cost me in terms of SST? And if you look at that, well, you actually need quite a big SST anomaly over the Pacific compared to the Atlantic, which means that we're more sensitive to the Atlantic than we are to the Pacific, right? But then again, the anomalies in the Pacific are much bigger, right? Now, if you ask this in terms of miles per gallon, right, you get a much more complicated thing, because then you have something, well, here you're normalizing by the variance of the precipitation, just in this box here, right? So it looks like that map. These maps look similar, right? Here you're normalizing by the variance of the temperature, which is a function of position, right? So these maps don't look the same. And what you're asking is, I know how much SST anomaly I've got, how much rainfall is it going to give me in millimeters per day, right? And here you see that what's plotted here in color is not the SST anomaly, it's the rainfall. So at every position on this map, we're plotting the rainfall in northeast Brazil for a given SST anomaly, right? So that's a bit more difficult to interpret. Let me say that again, okay? Every position on this map, the scale here is in millimeters per day. Every position on this map is plotted as a rainfall rate. But it's not the rainfall rate in the position on the map. It's the rainfall rate in northeast Brazil every time, okay? And it's plotted in the position of how much that would be if you had a 1 degree SST anomaly in that position. So this is reminiscent of what you call an influence function, okay? And but it's just statistics. It's not causality. Be careful with that because the data are not independent from one position to another, right? So we can't just interpret this as causality. All we have is data. And yet we also have a model, right? And with the model, we can do causality. So let's try it. This is DREAM, and I have just added a heating anomaly here in this 1 pixel. Well, actually, it's 9 pixels. But and I run the entire forecast system for 4 months with 38 member ensembles, just with a heating anomaly of 1 degree per day switched on in that position, and compare it with the control. And what happens is, well, you get this signature over Brazil, right? So what happens if we do that for every one of these boxes in the tropics, okay? We'll collect a whole set of responses over Brazil. And that will be, now I can't show you that on the screen, but for those of you who actually took trouble to come here in person, I'll show you on my iPad, all right? So we're going to use every position here. And you see, I don't know if you can see, the kind of blue patches swimming around the world here. Each one of these frames of this movie is a 4-month, 38-member ensemble seasonal forecast, right? And pay attention to what's happening over Brazil. I want you to memorize every single one of those frames, okay? We've got 128 plots here, right? So actually, this experiment is much more costly on the computer than doing all the hindcasts, right? There's 128 4-month, 38-member ensemble seasonal forecasts, 128 of them. So this, I tried to do this on my laptop in Fortaleza, where it's hot. And that's why I don't have a laptop anymore. I have this iPad, right? Because it fried my CPU. And in the end, I just asked Junior to do it, which I should have done in the first place, on the Funsemi computer. And after he'd finished, this, that's just, you know. After he'd finished, he got this. So what this is the response in terms of rainfall in this box, plotted in the position of each one of those heating anomalies in each experiment. So this is an influence function. And obviously, if you heat directly over Brazil, it's going to be wet directly over Brazil. If you heat over the tropical Atlantic, apparently it's dry over Brazil. If you heat so basically that's this influence function from the model, one would hope would look like this regression analysis I showed you before. And it doesn't. Well, that's not a big surprise because this is with heating anomalies. It's not with the SST boundary condition, right? And I've just spent half an hour showing you that that doesn't work, right? So what we've got to do next is to repeat that with actual SST anomalies. And I'm sure we'll get a result which will look much more like this, right? Because I know that the forecasts work better, right? So this is work in progress, but this is exciting because, as I said, to do a seasonal forecast with DREAM, With ECAM, it takes a week. With DREAM, it takes a few hours, a couple of hours, 3 hours. How about if I take, when this is working, take this influence function and just multiply it by the SST anomaly on the 1st of January, and within a fraction of a second, I've got a seasonal forecast, right, for that year. So this is a linear model of my dynamical model, and it will run incredibly fast. Within seconds, I can do the entire hindcast run. That's what we're going to do next, to see how well that compares with the actual model. So what do I expect? Well, I don't know. I've given up on expecting anything, right? But what I hope is that it's good, but not quite as good as the model, right? If it's rubbish, then it's a waste of time. If it's better than the model, that's depressing. If it's good, though, it's very useful, right? So post-race analysis, well, we've adopted a more conventional Aston Martin-like approach to our race car, and it works. The forecast where DREAM still performs badly seem to be associated with a lack of correlation in the Atlantic. The Atlantic is a difficult nut to crack. I think the Pacific is, El Nino is pretty straightforward. I think the Atlantic is difficult. We can do hindcast with individual ocean basins. That's easy. We've done it already. And then this is just what I've been talking about the influence functions, which will give us a handy linear model of our simple GCM, right? And finally, I hope that Toto and Lewis improve as much as we have and stick it to Red Bull before the end of 2023. That's it.
Perguntas, questions.
Pode ser em português.
Pode ser. Ele pode responder em português também. Um pouco mais lento, mas ele responde. Alguma dúvida sobre, ou só dúvidas? Ou só muitas dúvidas?
Dúvidas.
Dúvidas. Questions. Alguma? I have one simple. You compare your model with ECAM 5, yes?
Yeah.
But your model is very low resolution, both in space and in the vertical. Do
Not
you have
so-
31 waves, no?
Not so much. Yeah, we have a version of DREAM with T42, which is the same as ECAM. And we for other reasons, we went back to T31. Doesn't make much difference to the
Okay, but
the
the resolution impacts the time of processing.
Oh, yeah.
How refined is the ECAM 5, the ECAM that
They use ECAM at T42. Right?
T?
42.
Yeah.
Yeah. And
It's low resolution also, no?
yeah, well, it's lower than it's higher than T31. Well, we found going from T42 to T31, it goes twice as fast and it uses half the storage. So that was a big advantage. So
Okay.
we thought in terms of the quality of the dynamics, it's not much different, but it's just quicker, right? So,
Did you try to compare the boats?
yes.
31 with 42?
Yes, we spent a long time doing that. Yeah.
Okay.
Doesn't make a huge amount of difference in the tropics, but I have other projects with the mid-latitudes where there are systematic errors in the T42 version, which are a pain. So T31 is the sweet spot.
Okay. Copy. Okay. No. Vocês entenderam que é difícil fazer previsão sazonal? Okay, so
If anybody is interested in using DREAM, then just contact me or Tessio. There's a user manual, there's a website, there's a GitHub. So,
se alguém quiser usar para fazer alguma pesquisa, para contatar eles. Hã? Quem está aí no meeting tem alguma questão? Nilson?
Apenas parabenizar o professor, excelente trabalho, uma contribuição fantástica para a gente buscar melhoria nesses processos aí de projeção climática. Parabéns, obrigado. Thank you.
Obrigado.
Okay, thanks, Nikki.
Okay,
I
thank
hope
you.
to see you soon.
Yeah.
Return here.
Every chance I get.
Thank you. Obrigada aí vocês também por terem vindo. Está anotado aqui no papelzinho. Vou negociar presença em dobro, hein? Tchau, gente.